Next up is our quotient rule, which is what we use when we have two functions dividing each other. And with this one, order is very important between two things. We have subtraction here, so the order with subtraction matters. It also matters which functions are numerator function and which ones are denominator function. So what I find with this rule is that it is difficult to memorize if I'm just thinking of f of x and g of x, or numerator denominator. So that's why we have this kind of shorthand here that we like to use. And you'll hear me whisper this to myself during the videos or if you come to student hours, because this is how I think of it. So we have our high function and our low function. So when we take the derivative, we're going to take our low function d high. So that means we're taking our lower function times the derivative of the numerator function, minus high d low, so our numerator function times the derivative of the denominator, all over low low, which is our denominator function squared. So low d high minus high d low over low low. All right, so let's try this out. And let's see how many, we have equation of a tangent line and just the derivative function. Okay, so this is what I'm calling my high function and my low function. So how I would write this out, and again, I'm just going to show the step for before I even take a derivative, just so you can see what's landing where. So we're going to end up with this big fraction, and we're going to go low d high. So low is the 2x cubed plus 3. D high means I'm taking the derivative of the 5x squared minus 1. And then we're going to go minus high d low. So 5x squared minus 1 times d low, so the derivative of 2x cubed plus 3. All over low low, which is taking that 2x cubed plus 3, is staying in the denominator, and we're going to square it. Again, if you're wondering why this rule is the way that it is, there's lots of proofs out there, and again, it's all coming from that limit definition. I just like to keep mentioning that because students will often be like, where, how, why, how, what? So the proof is out there if you want to look it up, but it all comes down to this rule right here. Okay, so now I'm going to start taking the derivative. So I have that 2x cubed plus 3 times the derivative of the 5x squared, so 5 times 2 is 10, x to the 2 minus 1 is 1, the derivative of the negative 1 turns into a 0, minus the 5x squared minus 1 stays the same, derivative of the 2x cubed plus 3, so 2 times 3 is 6, x to the 3 minus 1, which is 2, and then the plus 3 turns into a 0. All over 2x cubed plus 3, all being squared. Now, my tips for simplifying these, because again, taking the derivative tends to not be the real tricky part. It's simplifying the derivative function down can be the tricky part. And my recommendation for these is leave the denominator factored unless if there's something to simplify inside. Like if I looked in there and could see like a difference of squares, or if I could see like a common factor that could be taken out, then I would start dissecting that. But what I'm looking at here with the 2x cubed plus 3, I don't see anything that I can factor within that pairing there. So I'm going to leave it like this, just in case, as I'm simplifying with the numerator, I may end up with a common factor that I can cancel. Oh, that reminded me. Big thing here, the subtraction. Let's do a quick refresher of good canceling and bad canceling. Because of that subtraction right there, that is grouping those two pieces together, which means I cannot cancel out that 2x cubed plus 3. I know it's so tempting because you see it right there, but we could only do that if 2x cubed plus 3 also showed up in this term over here. So it has to be a common factor across the two terms there. So you're going to see this every single time. You're going to have this factor here and this factor here, and you're going to want to cancel, but you can't. And it's because of that subtraction there. Subtraction and addition always makes it tricky to cancel things. Even at the beginning here, like you would maybe want to cancel something there, but we can't because of the subtraction and addition. It creates this grouping where really all that's together as a 5x squared minus 1, all of that's together as a 2x cubed plus 3. And the only way they could separate things up to cancel is to factor. So be very careful with canceling, and that you are not canceling across addition or subtraction unless that thing is a common factor within each term that's separated by addition and subtraction. All right. I'm going to keep mentioning that one because that's a rule that's very, very important. All right, so my next step is going to be to simplify the numerator. So I'm going to distribute the 10x in, so 20x to the fourth plus 30x minus, and I'm going to go ahead and keep parentheses here for a moment, so distributing the 6x squared, so 30x to the fourth minus 6x squared. And I just kept the parentheses there for a moment so I could really see that negative is going to distribute through. Let's go ahead over here. So I have that 20x to the fourth plus 30x minus 30x to the fourth plus 6x squared over 2x cubed plus 3 squared. And we're going to end up with the final answer of a derivative function. Let's see, 20 minus 30 is a negative 10x to the fourth plus 6x squared plus 30x over 2x cubed plus 3 squared. Now, something else I would do here is I would look and I could see, ooh, I have a common factor of 2x there. So I could even do like a negative 2x out of that numerator, which would leave us with a 5x cubed minus 3x minus 15. And I could see about factoring that. And really, all I would care about is getting a possible factor of 2x cubed plus 3. But I'm not seeing that come out of this. So really that work is not necessary. So I'm going to leave it just like this as the derivative function. But if we can cancel things with the denominator we want to, it's very satisfying when it does happen. But I will say it doesn't happen all that often. But no matter what, we want to try. So we want to get to this kind of completely simplified part. If we can cancel, we'd cancel. If you want to express this in completely factored terms, you can go a step further with taking out that negative 2x. So you can see that 5x cubed minus 3x minus 15. So you can really see that nothing's going to cancel out, but either form is good for me. Okay. One more example here, and we're going to find the equation of the tangent line. I will say what's nice about finding the equation of the tangent line is the simplifying is a little more straightforward. Because our function, so f of x is equal to 4x over 1 plus x squared. We want to fill in the blank for this y equals mx plus b for this tangent line. We don't really care what f prime of x is. It's important. We need to take the derivative. I should say that. The derivative is important. The derivative function is not important. Meaning finding this function that represents the derivative of any point given some value of x. We're only interested in one derivative. And for us, in this case, we're just interested in what's happening at -1. So what we can do here is evaluate this derivative, but just focusing on -1, and that'll make the work a lot simpler the sooner we jump to that. Instead of taking the derivative function and simplifying, we can just start right here. So let's see how this looks. I'm still going to apply the quotient rule because I have high and low. So I'm going to go low, which is 1 plus x squared, but what I can do is go ahead and plug in negative 1 squared. Okay, I'm going to take back what I said a little bit. We're going to do the setup with x, because it gets incorrect if we have the number in, so sorry. Got a little too excited about the trick. It'll still be easier, but we are going to start with x there for like 2 steps, and then we can switch over to the numerical value. So low, 1 plus x squared, d high, derivative of 4x, minus high d low of 1 plus x squared, all over low low, 1 plus x squared, all squared. Okay, then I'm going to take the derivative. So I have 1 plus x squared times 4 minus 4x times 2x, all over 1 plus x squared times 2. Okay, this is the stage I was talking about where we would start multiplying out and simplifying, but my recommendation is it doesn't matter how this looks simplified because we're just going to plug negative 1 in. So now let's do that. Even while it's unsimplified, in fact, it's even better unsimplified because there's less chance of us making errors there. So we're going to go 1 plus negative 1 squared times 4 minus 4 times the negative 1 times 2 times the negative 1, all over 1 plus negative 1 squared, squared. And then we simplify. So let's see, 1 plus 1 is 2 times 4 is 8, minus 4 times the negative 1, so positive 4 times the negative 2 is negative 8, all over 1 plus 1 is 2, and squared is 4. So we're getting a derivative of 4 out. So we have y equals 4x plus b, and to find b, we're going to plug in our coordinate with y equals negative 2, x is negative 1. And that'll be a negative 2 equals negative 4 plus b. Add 4 to both sides for a positive 2. And just for the sake of all the rules we're applying there, let's check our answer with this one. So to check our answer, I'm going to go to the graphing calculator. I'm going to graph our function 4x over 1 plus x squared. I can even, let's go ahead and plot the point to the negative 1, negative 2, so we can see right where we're at. And then our equation of the tangent line that we found is a 4x plus 2. Uh-oh. I moved too dang fast because that should be a minus 8. And that's where it's good to graph and check your answer, because that'll be a 0 with a slope of 0. So with this, let's go ahead and get rid of that and make our corrections. Y equals 0x plus b. So we're just going to be y equals negative 2. So we're just going to go like that. And that makes more sense because we're at a relative minimum there. So we're going to have a flat line going through that negative 2, going through that y coordinate. I'm going to leave that in. It's a good example of checking your work and then making the corrections.